Hi everyone, welcome back. In this section we're going to look at the directional derivative and the gradient vector. So let's get a feel for where we are so far in terms of derivatives. So I'm going to imagine we've got some surface in space. So we've got our coordinate axes. Let's maybe extend this axis out. So x-axis, y-axis, and our z-axis. We've got a point on our surface. And we're interested in a couple of things at this point. So for example, what is the rate of change in the z value as we move in the x direction through this point? So if we think about what we've done so far, we've imagined that we're standing at a point in the plane, in our domain, and we move a little bit in the x direction. So that allowed us to take a slice of our surface in the x direction. That produced a curve, and for that space curve we constructed a tangent vector. That tangent vector had components, so for a unit change in the x direction, the change in the the change in the z direction was given by the x partial derivative. So this is really indicating that if we're moving in the x direction from this point in the domain, f sub x tells us how our z value is changing. Do the same thing in the other direction, in the y direction. So imagine slicing our surface in the y direction, so that is, we construct a plane parallel to the yz plane, slicing our surface. From there we can construct the tangent vector. The tangent vector is given by 0, 1, and then the y partial derivative. Now we ask the question, what happens if we move in an arbitrary direction from this point? So for example, if I move in some direction u, so we already know that if we move in the I hat direction or the j hat direction, that our z value changes at a rate of either the x partial derivative or the y partial derivative. What happens if we move in some arbitrary u direction? Well, the same thing happens in the sense that we just slice it with a plane in that u direction. That constructs some curve. From that space curve we can construct a tangent vector, and the rate of change in the z value along this curve is what we call the directional derivative. So we would have, if this was vector AB, so we're going in the AB direction, where u is unit length, so it's a unit vector, then our tangent vector would be AB, and then there's some value that would go there. That would be how the z value is changing as I move in the direction of this unit vector u. The value that goes here, this is what we're going to call the directional derivative. It's how the z value is changing as we move in the direction of this unit vector. As our inputs move in the direction of the unit vector u, that quantity there would be how the z value is changing, and that's what we're going to call the directional derivative. If we move in the x direction, that's the x partial. If we move in the y direction, that's the y partial. If we move in this arbitrary direction u, that's called the directional derivative. As a visual for this, we can have a look at our surface and slice it with a plane. In this case, our plane is in the x direction. And so the vector down below is showing the direction that the plane is being sliced in. You can think of that as the unit vector in the direction we are slicing the plane in. And then up above, what we have is our vector that's pointing in the direction that the curve is going in at that point. In some sense, this is related to the directional derivative. So now as I change the direction, of my plane that slices it, that vector that's tangent to the curve at the given point, so that vector that's up on the surface at the given point, that's changing direction. And the z component of that vector is really measuring how the z value is changing if I move in the given direction. And that's what this directional derivative is trying to capture, how the z value changes as I move in various directions. Okay, so that's the first thing we want to describe and define formally, and then we want to learn how to compute it. The other thing that's going to come up is this relationship between these derivatives that we're going to compute and the level curves associated with that multivariable function. So let's just take a peek at what we know about level curves, maybe build some intuition, and this will be the sort of the second side, or the other side of the coin that we'll be investigating today. This is related to the gradient vector. So the title of today's lesson is Directional Derivatives and Gradient Vectors. We've just indicated what a directional derivative is supposed to be, and we'll have to describe it formally and then figure out how to calculate it. And the next part is this thing related to this idea of a gradient vector. So I won't introduce the gradient vector here, but what I will introduce is this idea of we've got a level curve, and I've got some point on the level curve. And I'm saying, suppose we stand at this point, in which direction is the steepest ascent? So this is a topographical map of Burnaby Mountain. You can see these level curves here. These level curves are curves of constant elevation. And we know that the center of this map is the highest elevation, that's Burnaby Mountain. And then as you move to the outside of the map, the extremities, that's becoming closer to sea level. So the question is, if I'm at this point P, which direction is the direction of steepest descent? So I'm going to zoom in on it. And the main idea is that if I move along this curve, well, that's a level curve, so my elevation would not change. So if I move in that direction, or if I move in that direction at that point P, my elevation won't change. I'll remain at the same elevation because I'll be traveling along a level curve. So what direction do I need to go in to get the direction of steepest descent? Well, at least intuitively, we should probably travel at a direction that's perpendicular to the level curve at that point. And that should be the direction of steepest descent. Level curves are to my left and right, so that means dead ahead is steepest descent. And then we can start doing that at each point we encounter. Construct a right angle, cross the level curve at that right angle, and that seems to be the direction of steepest ascent. So we're getting right angles at each of these points. And so that seems to be our trail that's going to force us to have to climb the fastest. Right? We're sort of going in the direction that the mountain is rising up in front of us the quickest. All right, let's see how that will come into play through our discussions today. So let's come back to this idea of a directional derivative. So first we'll recall our partial derivatives and their definition in terms of a limit. So the x partial derivative is the limit as h goes to 0 of, we got f of x naught plus h minus y naught minus f of x naught y naught all over h. So what's happening here is we are nudging just a little bit in the x direction, taking our z value there, subtracting off the z value, the place we started at, and seeing what the rate of change is. So divide by the change in our input to see what our rate of change is in our z value relative to these changes in the x value. So this is the x partial derivative. If we wanted to find the y partial derivative, we just nudge ourselves a little bit in the y direction and compute the limiting value as h goes to 0 of this difference quotient. What if we want to go in a direction that's not just entirely in the x direction or the y direction? We want to go in an arbitrary direction. how do we define the derivative in that case? What would be a natural way to define it? So here we want to go in this arbitrary direction. Well, what we do is figure out where we're starting from. Now, this is our point in the plane x naught, y naught. Instead of going entirely in the x direction or in the y direction, what we do is we head off in some u direction. So that's a unit vector u. And we just go a little bit in that u direction. So I'm going to multiply it by some h value, which we're going to let h go to 0. That gives us this new point. What's our new point? It'll be x naught plus HA, y naught plus HB. We sample our function value there, so in other words we take f at that point, and we look at the difference quotient. So the f at this point minus f at the starting point divided by h. So that's what we've done here. We've nudged ourselves a little bit in a direction that's a combination of the I and j directions. So we moved a little bit in the x direction and a little bit in the y direction. And how much depends on the relationship between a and b to each other. When we take the limiting value of this expression as h goes to 0, that gives us the rate of change of z in that direction. So that's our directional derivative of f at the point x naught, y naught in the u direction. So the question we can ask now is, how do we actually calculate this? How do we calculate du f x naught, y naught? How do we calculate this directional derivative? So that's our limiting definition. It would be nice if we could use differentiation rules to calculate the derivative, and in fact we can, and we'll see how it's related to the partial derivatives, the ones above. So here's how we can calculate it. What we'll do is we will let g of h be a function of just a single variable, h. And that function is going to be f of x naught plus HA, and then y naught plus HB. So we define this function of a single variable, g, which is basically just a function value, f, where we've moved a little bit away from x naught, y naught. We've moved basically h units away in the u direction. So that's what g is calculating. And now what we will do is, maybe we'll put a comma, then find or calculate or compute g prime 0 in two different ways. So we've got this function of a single variable. Let's compute its derivative at 0 in two different ways. We do it in two different ways because if I compute its derivative in one way, get some expression for it, do the derivative in a different way, get another expression for it, well, those two quantities have to be equal to each other because they are both the derivative g prime of 0. And so we can get a quality of two expressions by constructing them in two different ways where they represent the same quantity. So here's method number 1 of finding g prime of 0. We'll go right to the definition. What is g prime of 0? By the definition of derivative, it's the limit as h goes to 0 of g of 0 plus h minus g of 0 all over h. And what is that? Well, g of 0 plus h, that's just g of h. So that's f of x naught plus HA, y naught plus HB minus f of x naught, y naught, that's g of 0, all over h. And that's just the definition of the directional derivative. So the nice thing about defining g to be that function of a single variable u, or single variable h, sorry, is that when we compute its derivative at 0, it's precisely the directional derivative. Okay, now let's compute it in a different way. Method number 2 for computing g prime of 0. Now we'll go to our techniques for calculating derivatives. G prime of h. So I'm looking up here at g of h, And I'm saying, well, that's a function of two variables. The outer function, f, is a function of two variables, but the inner functions are each, so the x function and the y function are each functions of h. So I can use the chain rule to do this. So I'll indicate CR for chain rule. So it's going to be the derivative of f with respect to x times the derivative of x with respect to h, plus the derivative of f with respect to y, plus the derivative of y, times the derivative of y with respect to h. And so what is that? Derivative of f with respect to x. Well, that's our f sub x, so I'll just leave it as df dx. And what is the derivative of x with respect to h? Well, our x function of h is x naught plus ha. X naught's a constant, a is a constant, so this is a linear function of h. So when I take its derivative, it just gives me the value a. And then I've got df dy times, and then we've got this other piece, y naught, hb. That's our y function, and its derivative is going to be b. So what we have here is that when I specify it precisely at the moment when h is 0, the derivative is going to be the partial derivative of f with respect to x at the point we are interested at, x naught, y naught, times a plus the partial derivative of f with respect to y at x naught, y naught, times b. And so there's an alternate expression for the derivative g prime 0. So between parts 1 and 2, we've computed g prime of 0. We get two different expressions for it. They have to be equal. So therefore, we have that the directional derivative of f at x naught, y naught is equal to the partial derivative with respect to x at x naught, y naught times a plus the partial derivative with respect to y at x naught, y naught times b. And so there we have derived a way to compute this directional derivative. It involves knowing the partial derivatives, the x partial, the y partial, and multiplying it by the x component and the y component of that unit vector u in the direction we want to compute the derivative of. So that establishes this theorem down below. We've just proven it. If f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u, and its value is given by the x partial times a plus the y partial times b. Moreover, we can recognize that this product really looks like a dot product. I mean, if we look at this, it looks like it's a dot product of two vectors. The second one looks like it's AB. The first one is f sub x, x naught, y naught. Okay, I didn't leave myself nearly enough room, so I'll space that out a little bit. And the second component of that first vector is the y derivative, x naught, y naught. So that's what that expression for the directional derivatives look like. This is our vector u. This, well, it'd be nice to have a name for that vector that consists of the two partials. So that we call the gradient, and we represent it by this upside down triangle with an arrow on top with f next to it. So we call this the gradient of f, and that's at x naught, y naught. And that means we can write our directional derivative. Actually, I'll write it up in the statement of the theorem itself. We can write it as, now this nice shorthand, the gradient of f at x naught, y naught dot the vector u. So there's our formal definition of the gradient. I've introduced it above. I didn't even call it, or write down the name of it here, but I can write it down here. Gradient vector, that's what we call this. And there's the formal definition. If f is a function of two variables, then the gradient f is the vector function, which we denote by that upside down triangle f, and we read that gradient of f, or grad f. and it's defined just to be the vector of partial derivatives, f sub x and f sub y. So let's have a look at an example where we compute a gradient. If f is given by x squared minus y squared, let's A, find the gradient of f. Okay, so the gradient of f would be just the x partial and the y partial. So that would be 2x and negative 2y. So that's it, there's our gradient. And that wasn't at a particular point, this is just the general gradient at any point x, y. And we also want to find the directional derivative at a particular point in a particular direction. So we want to find a directional derivative in the direction of v. We need a unit vector in that direction because our directional derivative depends on the fact that our direction is defined by a unit vector. So unit vector in direction of r, or v, direction of v. So what is that? We'll call that u, and that's just v over its magnitude, or 1 over root 2, 1 over root 2. And now we can go ahead and compute the gradient of f at the point in question, 2, 1. So that would be 2 times 2 minus 2 times 1, or 4, negative 2. So there's our gradient of f at the point 2, 1. And now we want to find the directional derivative, d in the direction of u, f at 2, 1. So that's the directional derivative, that's what we want to compute. And we know that that's the gradient at 2, 1 dot the unit vector. So that would be the gradient for negative 2 dot 1 over root 2, 1 over root 2, which has a value of 2 over root 2, or root 2. So there's our directional derivative. So that means if we're standing at the domain, at the point in the domain 2, 1, and we move in the direction of v, then for every unit change we move in the direction of v, our function value should change by a value of root 2. It should increase by a value of root 2. So I like to think about this, in terms of a concrete example. You can think about it as temperature. For example, if my function is giving me the temperature at a particular point x, y, then that's telling me that if I'm standing at the point 2, 1, I can compute my current temperature, and then if I walk in the direction of v, the direction v is pointing me in, every unit movement I make, every step I take of length 1 in the direction of v, I will feel a change in temperature, an increase in temperature of a value of root 2. So this is telling me how my function values are changing when my inputs move in the direction of v from the point 2, 1. All right. Now that we have this idea of a gradient vector, and we can see how it's useful. For right now, it's just been a bookkeeping thing. It's just a way to keep our two partial derivatives in a single object, which we call the vector, and that allowed us to compute directional derivatives as a dot product. We may want to think about what the geometric properties of this vector are. And here are the two main properties that this vector of partial derivatives has. The gradient vector points in the direction of steepest change. So that comes back to the topographical map we had of Burnaby Mountain. That direction of steepest change, it turns out it actually was related to the gradient of the function that gave the surface of the mountain. So gradient points in the direction of steepest change. That's this picture on the left. These directions that we're moving in are always the direction of steepest change, and they are what the gradient vector will be. These are the directions the gradient vector points in. What else do we know about our gradient vector? Well, if we look at the level curves of our surface, it turns out that the gradient vector is orthogonal to our level curves. So you can see that from the picture on the right. Our level curves are shown in green, and our gradients are shown as those orange vectors, and they're perpendicular to the level curves. So let's verify these two facts. So we want to show that the gradient points in the direction of steepest change. By steepest change, it means the maximum rate of change that the function value has. So that's really about the maximum value the directional derivative can take on. So let's first write down what the directional derivative is. So our directional derivative is given by the gradient at the point in question, dotted with the direction. And we're interested in what direction, what value for the vector u is going to make the dot product as big as possible. Well, we know how big this dot product is because the magnitude of a dot product is just the magnitude of the two vectors, so it's the magnitude of the first times the magnitude of the second. The second one's a unit vector, so its magnitude is 1, times cosine of the angle between them. So this means that the directional derivative is maximum when cosine of theta is maximum. So when cosine of theta is 1. And that happens when theta is 0, which means that u is in the same direction as the gradient. So in other words, the derivative is maximum when the direction you take is in the direction of the gradient. So the direction of the gradient points in the direction of steepest change. So that just proves that first point up here. Grad f points in the direction of steepest change. What about the other statement? Grad f is orthogonal to the level curves. Let's see if we can verify that. So I'll leave that one visible up top. So what do we do there? So let's consider a level curve. So what would that be? A level curve would be something of the form f of xy is equal to some constant k. So that would give us one of these curves in the diagram, let's say on the right, where the k values are indicated. So the k equals 0 value is this sort of x-shaped region. The k equals 3 value, I'll just draw it in here. There's a k equals 3, it's that one, and this one over here. So there's our k equals 3 level curve. We got a hyperbola there. And so for various values of k, we get these different shapes, different shaped curves. And so let's just consider an arbitrary curve, f of xy equals k. Let's let r of t be a parametrization of the level curve. So that'd be like this curve corresponding to k equals 3 in the picture above. R of t would be a parametrization of that curve, whatever it is. So it's an arbitrary parametrization of a curve. And now what we're interested in is showing that the gradient vector is perpendicular to the curve. So I want to show that the gradient vector dotted with the tangent vector to the curve is 0, because that would show us that the gradient vector and the tangent vector are perpendicular, or in other words, the gradient vector is perpendicular to the level curve. So let's first write down what it means to be a parametrization of the level curve. It means that if I plug that into our function, then a constant will come out. K will come out. For every value of t, k comes out because that's a parametrization of the level curve. All those points plugged into the function return the same output. So now we can differentiate that equation. And when I differentiate, I'll use the chain rule. Outer functions are functions of two variables. The inner function, there's an x component for our parametrization, a y component for our parametrization. Each of them are functions of t. So when I do the chain rule, it might take you a second to see this, but I can write it in a condensed form. It's really the gradient at r of t dotted with r prime of t. And that's equal to 0 because the derivative of the right-hand side, k, is 0. So you may be looking at this saying, I don't remember the chain rule having a gradient and a dot product, but if you think about what the chain rule says, it says differentiate the outside function, df dx, multiply by the derivative of the inside, dx dt, and then do the same thing for the next component, df dy, dy dt. But I get a df dx and a df dy, those two terms, and each of them is multiplied by dx dt and then dy dt. So that's really just the dot product of these two things. It's the dot product of the partial derivatives, df dx, df dy, with r prime of t, dx dt, dy dt. So the chain rule really can be expressed in terms of this dot product. And what this means is that the gradient of f is perpendicular to r prime. And so if the gradient is perpendicular to the tangent vector, it means that the gradient is perpendicular to the level curve, because the tangent vector is parallel to the level curve. It's the direction the level curve is going in. So we get that the gradient vectors are perpendicular to the level curves. So those are our two main geometric properties of the gradients. A gradient tells us the direction we should go in order to get the most rapid rate of change in our function value, and the gradient is perpendicular to the level curve. In some sense, these are mutually compatible with each other, in the sense if I look at my diagram on the left, and I'm at a point, let's say I'm at this point here on the left, which direction do I have to go in to get the steepest rate of change? Well, if I went this way or this way, I'd be going along the level curve. So I have to go at a direction that's perpendicular to the level curve in order to get the most rapid rate of change. And so that means I'd have to go in this direction, perpendicular to that. And that's really what the other picture was saying, that the gradient is perpendicular to the level curve. So in some sense, these are really they're compatible with each other. They're telling us really about the geometry of the gradient vector. Perpendicular to the level curve and points in the direction of steepest change. You may say, what's the direction where the directional derivative is minimum? That could be a question. So you want to know, which direction do I have to go in to get the maximum rate of change in my function? That would be the direction of the gradient vector. What if I wanted to go in the direction where the change was minimum? And that would be in the opposite direction. You would go in the other direction. And the one way to think about this is, if I'm thinking of this as a mountain, then I'm climbing the mountain. I'd go perpendicular to the level curve to go ascend the mountain as quickly as possible. But if I wanted to drop my function values to drop as quickly as possible, then I'd go in the opposite direction. I'd descend the mountain. So I'd climb down it essentially. And so I just go in the opposite direction. So negative the gradient is a vector that points in the direction where the directional derivative is minimum. All right, let's go ahead and look at a statement of that. So the maximum value of the directional derivative, suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative is given by, so this is now the maximum value of the directional derivative, is the magnitude of the gradient vector. So not only does the gradient vector point in the direction of maximum change, its magnitude is the maximum value of the directional derivative. And it occurs when u has the same direction as the gradient vector. So that's just summarizing what we got above. In fact, it's just summarizing this statement right here, that the directional derivative is the magnitude of the gradient times cosine, and that's as big as possible when theta is 0. Okay, now we can take these ideas and just go up in dimension. If we had a function of 3 variables, f of x, y, z, where f is a differentiable function, then we can take the gradient vector of that, and that's just made up of the 3 partial derivatives, f sub x, f sub y, and f sub z. We can define a directional derivative in a direction of a unit vector u. It's defined in exactly the same way, and we can compute it in exactly the same way as well. This would be the gradient vector at x naught, y naught, z naught, dotted with the unit vector. That's how we could compute it. There's a nice succinct way or condensed way to write that definition of the directional derivative, where I don't have to constantly write out the three components each time. I can just say let x naught with the vector symbol on top be that initial point, x naught, y naught, z naught, and u be our unit vector in the direction we want to take the derivative with respect to, and so I can write it in this nice condensed form. And so that also allows us to then just say that we can do this for any vector. It doesn't have to be of dimension 2 or dimension 3. We can do it for any number of dimensions and the formula still looks the same now that we've expressed it in terms of vectors. And we've just summarized down there how to compute it. I've already indicated up at the top, but this is how you would compute the directional derivative. It's the gradient dotted with the direction vector. So let's go ahead and do an example. So if f of x, y, z is x e to the z plus y, z, find the gradient. Okay, so the gradient of f is given by f sub x, f sub y, f sub z, which is e to the z is the x derivative, z is the y derivative, and x e to the z plus y is the z derivative. So there's our gradient. We want to find the directional derivative of f at that point in this particular direction. So let's find the unit vector in the direction of v. That would be v over the length of v, which is, what's the length of v? Well, v is 1, 2, negative 1, so its length would be 1 squared plus 2 squared plus 1 squared. So that would be 1 plus 4 plus 1, or 6. So this would be 1 over root 6. So there's our unit vector. Now we want to find the directional derivative of f in that direction at the point 1, 1, 0. So this would be the gradient at 1, 1, 0, dotted with the unit vector u. What's our gradient at 1, 1, 0? So that would be e to the 0, which is 1, 0, and 1 times e to the 0, which is 1, plus y, which is 1, so that would be 2. So that's our gradient, and this is dotted with the vector u. And so this becomes 1 over root 6, and then we've got 1 plus 0 minus 2, or negative 1 over root 6. So that tells me that if I'm at the point 1, 1, 0 in the domain, and I move in the direction of v, for every unit I move in the direction of the vector v, my function value drops by a value of about negative 1 over root 6. That's what this value is we've just computed. It also says, I mean, what we can glean from this as well is, if I'm standing at the point 1, 1, 0, and I want to know which direction should I go in so that the function value increases as rapidly as possible. Which direction should I go in? The direction I go in is the direction given by the gradient vector. So that tells me I should point myself in the 1, 0, 2 direction and move in that direction, because that's going to cause the greatest change in my function value. So if you're thinking about, you're in space, this is a temperature function, you're standing at the point 1, 1, 0, and you want to move in a direction where the temperature increases as rapidly as possible, point yourself in the 1, 0, 2 direction and start moving in that direction. That's where the temperature is going to increase as rapidly as possible. Any other direction it won't increase as rapidly. How about if you wanted to go in the direction where it decreased as rapidly as possible? Then you'd point yourself in the opposite direction, negative 1, 0, negative 2, and go in the other direction, and then the temperature would drop as rapidly as possible. Alright, that's it for the first part of this lecture, introduction of the directional derivative, gradient vector, how to calculate them, and a little bit of the geometry around them. In the second part, we're going to come back to this question of a tangent plane and look at it for level surfaces and do some examples there. So I'll come back in the second part to finish off this lecture. See you then.